All right, buckle up, everyone, because today we're diving headfirst into some pretty mind-bending cosmology.
Cosmology, yeah. Always a fun one.
You know it. Our listeners sent in some fascinating stuff about the accelerating expansion of the universe.
Oh, interesting.
And, of course, we can't forget the mystery of dark energy, what's driving this expansion, right?
Right. Always a big question mark.
Absolutely. And to really set the stage, they even sent in that paper about the 2011 Nobel Prize in Physics, awarded for the discovery of this accelerating expansion using distant supernovae.
Ah, the supernova data. That was groundbreaking stuff.
Groundbreaking is an understatement. But here's the real kicker. There's new research challenging this whole idea.
Oh, really? So are we throwing out dark energy now?
Oh, not so fast. Today, we're exploring an alternative explanation, something called the Timescape model.
Timescape model, huh? I'm intrigued. Lay it on me.
I knew you'd be into this. Okay, so before we jump into the Timescape model, let's quickly recap the current understanding of dark energy.
Sure, level set.
The prevailing theory, as you know, is that dark energy acts as a force with, wait for it, negative pressure.
Negative pressure. That's always a tough one to wrap your head around.
I know, right? It's like, how can something push outward with negative pressure? But hey, that's the current model. And this negative pressure is what supposedly drives the universe's expansion.
Okay, so we've got this mysterious force pushing everything apart. Where does this idea fit into our overall model of the universe?
Good question. It's all embedded within what's called the Lambda Cold Dark Matter model, or BCDM for short.
Ah, yes. ACDM, the reigning champion of cosmological models.
Exactly. It's the standard model we use to describe the universe. And within ΛCDM, the cosmological constant, represented by the Greek letter ochia, is how we account for this elusive dark energy.
So ACDLA is essentially the placeholder for this unknown force that's making the universe expand faster and faster.
You got it. But here's the thing. The CDM model, while it's been pretty successful in explaining a lot of observations, it relies on this negative pressure concept. And that's something we've never directly observed. It's like we're filling in a gap with something we don't fully understand.
So it's like a puzzle piece that kind of fits, but maybe not perfectly?
Exactly. And that's where these researchers from the University of Canterbury come in. They're saying, hold on, what if this accelerating expansion isn't a universal phenomenon after all?
Wait, so they're saying the universe isn't expanding uniformly everywhere? Now that's a radical idea.
That's putting it mildly. Their work suggests we might be misinterpreting something localized as a universal truth.
Misinterpreting, huh? So what are they proposing instead?
Okay, get this. Their timescape model suggests that the universe is made up of, well, think of it like a mixture. Some regions are densely packed with matter, like our own galaxy cluster, and then there are these vast empty spaces, what they call voids.
Okay, I'm visualizing this. Clumps of matter, and then these huge voids in between. Makes sense.
Right. But here's where it gets really trippy. They're saying that time could actually flow differently in these distinct regions.
Whoa, hold on. Different rates of time flow depending on where you are in the universe. Mind blown.
I know, right? So picture this. Within a galaxy cluster, all that densely packed matter, time might be moving at a faster rate compared to those vast empty voids.
So time is like a river flowing at different speeds depending on the terrain. That's a wild concept.
And because of this difference in the flow of time, we might be observing this apparent accelerating expansion.
So what we're seeing as accelerating expansion could just be an illusion caused by these different time flows. That's pretty radical. How does this timescape model hold up against the actual data, though?
That's the million-dollar question. The researchers actually use something called Bayesian statistical analysis to test their model. Bayesian analysis, good stuff. And they compared it to supernovae observations. And get this, the timescape model fits the data pretty well, especially for supernovae that are closer to us, what astronomers call having low redshifts.
Low redshifts, meaning those supernovae are closer and their light hasn't been traveling as long. I get it.
You got it. But redshift is a whole other deep dive, maybe for another day.
Agreed. Let's not get sidetracked. So the timescape model fits the data well for closer supernovae. What does that tell us about the bigger picture?
It's pretty significant because it implies that the timescape model might be more accurate at describing the universe's expansion on smaller scales.
Smaller scales. Interesting. Does this throw a wrench into that whole cosmological principle, the idea that matter is uniformly distributed across the universe?
Challenges it, definitely. If the timescape model is right and matter isn't spread out evenly, our observations of the universe's expansion could be way off.
skewed by our local time flow, essentially. So we might be thinking the whole universe is expanding at a certain rate, but it's
Hmm.
really just our little corner of it doing that.
That's the idea. And this isn't just theoretical. We've actually observed these massive structures in the universe that really make you question the whole uniform distribution thing.
Oh, you mean like those giant galaxy clusters and superstructures?
Exactly. There's the Great Wall, a galaxy cluster spanning 1 billion light years. That's massive.
Billion with a B. Hard to imagine.
Right. And then there's the huge quasar group and the Big Ring, all these structures that are way larger than what the standard model predicts for a universe with matter spread out evenly.
So these massive structures are like those puzzle pieces that just don't quite fit with the picture we thought we had.
Perfect analogy.
Yeah.
And their existence lends support to the idea that the universe might not be as homogeneous as we previously thought. It's all about clumps and voids with different time flows, potentially creating the illusion of uniform acceleration.
Okay, so we've got this timescape model challenging the concept of dark energy, reshaping our understanding of expansion, and even questioning the cosmological principle. Sounds like a pretty big deal.
It is, but of course, it's not without its own set of hurdles.
Yeah, there's always a but, isn't there?
Always. One of the biggest challenges is the complexity of this model. The timescape model is mathematically and conceptually way more intricate than the relatively simple CDM model.
So it's a tougher sell. Even if it's more accurate, people might stick with the simpler explanation.
It's possible. And these researchers have actually proposed similar ideas in the past, but they haven't gained much traction.
So they've got an uphill battle fighting against the established model.
They do. But to be fair to the ЛCDM model, it has been pretty good at explaining a lot of observations.
Yeah, it's not like we should just throw it out completely. It's still a useful tool, even with its limitations.
Agreed. Dark energy, within the context of the standard model, is still a valuable concept. But it's important to remember that science is always evolving.
Always evolving, absolutely. New evidence pops up. We have to rethink things, adjust our understanding. That's how science works.
Exactly. And who knows, maybe the timescape model will be the next big leap forward in our understanding of the universe.
Well, either way, it's definitely a fascinating challenge to the status quo, and that's what keeps cosmology so exciting.
I agree. It's all about pushing the boundaries of what we know, exploring new ideas, even if they seem a bit out there at first.
And sometimes those out there ideas turn out to be the ones that revolutionize our understanding of the universe.
Exactly. And that's why we love diving deep into these fascinating topics. Yeah, it's like we're trying to map the universe while standing in a funhouse mirror.
That's a pretty good analogy. It really does make you wonder, if the timescape model is correct, are we in a region of rapid expansion, or are we in one of those slower voids?
Right, like a cosmic slow motion zone.
Exactly. And if so, how would that affect how we perceive the universe's evolution? How would it change our understanding of how galaxies form and even the ultimate fate of the universe?
So many questions. It's enough to make your head spin. Does this timescape model offer any clues about where we might be on this cosmic map?
Well, the model itself doesn't give us a specific location, unfortunately.
Okay, no GPS coordinates for our place in the universe.
Not yet, at least. But remember how we were talking about the timescape model fitting well with supernovae data at lower redshift?
Right, the closer supernovae.
Yeah. The researchers think that might actually be a hint that we could be in one of those faster expansion zones.
So we're not just observing the universe's expansion, we're actually caught up in a cosmic fast track. That's a wild thought.
It really is. But again, more research is needed to confirm any of this.
Of course, science is all about testing and refining our understanding. And speaking of understanding, earlier you mentioned that our listeners sent in some material on the 2011 Nobel Prize in Physics.
Oh, yeah, that's right. That prize was awarded for the discovery of the accelerating expansion of the universe, which, as we've been discussing, the timescape model is now challenging.
It all comes full circle. But before we get too ahead of ourselves, maybe we should back up a bit and explain how that discovery was made.
Sure thing. So the discovery was made using observations of a very special type of supernova called type Ia supernovae.
Tia, okay. And what's so special about these supernovae?
Well, these supernovae are incredibly bright explosions that happen when a certain type of star, a white dwarf, reaches a critical mass. And here's the key point. Type Ia supernovae all explode with roughly the same intrinsic brightness.
They're like standardized cosmic fireworks.
That's a great way to put it. And because we know their true brightness, They act as what astronomers call standard candles,
Standard candles, meaning,
meaning we can use them to measure distances across the vastness of space.
oh, I see. So it's like if you had a light bulb and you knew exactly how bright it was, you could tell how far away it was based on how dim it appeared.
You got it. It's the same principle. The
Okay.
farther away the supernova, the fainter it will appear to us.
Makes sense. So these type I supernovae, they're like cosmic distance markers spread throughout the universe.
Exactly. And by observing these supernovae at various distances, essentially looking back in time, astronomers can piece together how the universe's expansion has changed over billions of years.
So what did they find when they looked at these distant supernovae?
Well, this is where things get really interesting. They found that the more distant supernovae, the ones that exploded billions of years ago, were fainter than expected.
Fainter, meaning farther away than they should be.
Exactly. It meant that the universe must have been expanding at a slower rate in the past than it is today. And that's how they arrived at the conclusion that the expansion of the universe is accelerating.
So these distant explosions, these standard candles, they reveal this incredible truth about the universe, that it's not just expanding, but expanding at an ever-increasing rate.
It was a truly revolutionary discovery, and it completely changed our understanding of cosmology.
And as we've been discussing, now we have this timescape model potentially shaking things up once again. It's amazing how science builds upon itself, how each new discovery leads to more questions and more possibilities.
It's a testament to the power of human curiosity and our drive to understand the universe and our place within it.
And speaking of that drive to understand, let's dive back into the implications of the timescape model. It's like we're peeling back layers of an onion, and with each layer, we find more complexity, more mysteries to unravel.
That's a great way to put it. And just when we think we've got a handle on things, a new discovery comes along and challenges our entire understanding. It keeps things exciting.
Absolutely. But even with all the excitement surrounding the timescape model, it's important to remember that it's just one of many alternative theories out there.
Oh, yeah, there are a lot of different ideas floating around about the universe and its expansion.
And it's crucial to consider all these different perspectives, to test them rigorously against observations, and to keep an open mind.
Absolutely. Science thrives on that kind of healthy skepticism and debate. It's how we get closer to the truth, even if it's always just out of reach.
Exactly. So are there any other areas of research besides these alternative models that you think might help us crack the code of the universe's expansion?
Well, one area that I find particularly exciting is the study of the cosmic microwave background radiation.
The cosmic microwave background, or CMB for short, right?
That's the one. It's essentially the afterglow of the Big Bang.
So it's like a baby picture of the universe.
Exactly. And by studying the subtle patterns and variations in this radiation, we can glean a lot of information about the very early universe, its composition, its geometry, how it evolved over time. It's a treasure trove of information.
Incredible. It's like using a time machine to peer back billions of years to the very birth of the cosmos.
It really is. And the more we study the CMB, the more we refine our understanding of the fundamental laws that govern the universe. It's amazing to think that we can even access this kind of information.
It is. And while we're talking about the big picture of the universe, we can't forget about dark matter. We've been focusing a lot on dark energy and the expansion of the universe, but dark matter plays a huge role too, right?
Absolutely. Dark matter is this mysterious substance that we can't see directly, but we know it's there because of its gravitational effects on visible matter.
It's like the invisible scaffolding holding the universe together.
That's a great analogy. It's thought to make up about 85% of the matter in the universe.
85%. So all the stars and galaxies and planets that we can see, that's just a tiny fraction of what's actually out there.
It really puts things in perspective, doesn't it?
It does, and it makes you realize how much we still don't know about the universe and the nature of reality itself. But that's also what makes it so exciting.
I agree. It's that sense of mystery and the constant pursuit of knowledge that drives us forward. It's what makes cosmology so captivating.
Well said. So as we wrap up our deep dive into the timescape model and the ongoing quest to understand the universe's expansion, what's the one key takeaway you'd like to leave our listener with?
I'd say it's this. Never lose your sense of wonder. The universe is full of mysteries, full of things we don't yet understand. But that's what makes it so fascinating. Keep asking those big questions. Keep exploring. Keep learning.
Beautifully said. And if you're looking for a great way to delve deeper into these topics, we highly recommend checking out resources like brilliant.org. Their interactive courses are a fantastic way to learn about cosmology, physics, and a whole range of other scientific fields. So keep those questions coming, keep exploring, and keep diving deep. Until next time.